Flown on in the Zorcloud. Hello, hello. How are you? Yeah, I think for VIPs, oh wait, yeah, hi to YouTube as well. For VIPs, I kind of do want to just try to keep it to like, I mean, I VIP'd Wombat because he drank paint. Now I'm not saying that other people are gonna have to drink paint. But in a few cases, I think there are probably some exceptions to be made, because yeah, there are the people who show up a lot, and I definitely want to have some way of recognizing them. Yeah, thank you for stopping by. Yeah, actually, I think it's only... Oh wait, actually no, I gave VIP to my brother because it's my brother, and that kind of just needs to be done, right? But yeah, it'll probably take a long time otherwise for those VIP slots to get filled in. It would take a really long time. Okay, so I talked to the staff scientist that was in my PhD lab, and I got his perspective on the field that I'm going into because he was in the same field, or like a similar field, and then got like his perspective on how things go, what people need to do in order to get a start in it, etc, etc. And yeah, also to get an opinion on whether or not my mini project idea was feasible. And he reminded me that, of course, yeah, I don't have to do something. I was already thinking about this, but I don't have to do something that is like very new science and would lead to something like a publication. I just need something that shows that I can do the work in the first place. So that's what I'm going to be aiming for. I don't know exactly how difficult things like the data cleaning are going to end up being like, because I haven't looked at what the data looks like. Unfortunately, yeah, I do kind of need to do the like hands-on data cleaning myself in order to see what it's actually like, and also to remember what all the commands were, because again, I ran through like a long time's worth of material with little experience in it within just a few weeks. So reminding myself about all those commands is going to be honestly quite a bit of trouble. And yeah, guys, thank you. Yeah, it's funny that I'm running into this without really knowing what I'm doing and how it's actually going to look. Because last week we got to see an example of this one paper, which I'll bring up again because I think I need to reference it. Not reference it as in cite it, but like reference it as in see what they did. And maybe that will help give me a starting point. So today's plan is for me to figure out the actual like specifics of what I'm planning to do. The main rundown is that different chemicals will have different what we call optical properties. So when it comes to things with light and these molecules, they all behave differently depending on what the molecule is. Surprise, surprise. Different things react differently. So there are quite a few different properties that you can take a look at. Most of these things stem from the fact that, let me see if I can like, is there like a online paint? Lucky. Okay, so I mean, I don't know how best to draw this out because it wasn't stuff that I worked on too much. This is not an accurate picture, but it's just what I'm going to use in order to demonstrate or to illustrate what I'm talking about. So these horizontal lines are how you usually represent energy levels for electrons. And in this case, I drew this like this one shape. There's also a corresponding down shape. These are up and down spin electrons. You don't really need to know exactly what that means. But yeah, electrons can have different spins, and for most stuff that we work with, we'll just draw them as like up or down spin. And there are different energy levels, higher level energies, that these electrons can be bounced up to. So let's say like we shine light on the molecule, and this light has enough energy to increase the energy of this electron so that it gets, say, like bumped up to a higher energy level. So this amount of light gives energy to the electron, and the electron goes to this new energy level. And then after that, given some time, the electron's going to probably give off some energy. So it's going to return back down to this original energy state. And because it's returning back down to the original energy state, this was a higher energy, and now it's going back to a lower energy. So if it goes from higher to lower, that means when it makes this transition, where does that energy go? Well, it's gonna have to leave somehow, and that's typically through light. So you shine light on the electrons. The electrons all like jump up in a bunch of the electrons will like jump up in energy. You might have like a bunch more up here, and then as they all lose energy and go back to the original states or like lower level states, those transitions all produce some light that comes out. And because we have different electrons and different molecules, and the molecules have like different levels of energy, like these levels and then these levels are all different, different energies. The amount of energy that it takes to bump this up, so this bumping up, and also the amount of energy that's released when it's going back down, those are all going to be different. And these can be like pretty characteristic of whatever molecules that you're looking at. So when you're actually doing these experiments, what this kind of thing would look like is a spectrum. So like when we talk about a spectrum, we can be talking about a light spectrum. So let's say the visible light spectrum. Let me get violet, or at least close to violet. So the visible spectrum is kind of like a rainbow. It's all the light frequencies that are visible to the human eye. Hopefully I have enough room here. I don't. Okay, we'll just pretend it's good. Okay, so the visible spectrum is all of the colors that we can see. So this is the visible spectrum. And depending on what part of the spectrum your light is from, it's going to have different amounts of energy. So over here, the red light has the lowest energy. And then on the violet side, this is the highest energy. And when you see like fireworks, or when you light certain salts on fire, and you see the colors that pop out, that's because those like changes in the energy levels for the electrons so we like spark it with fire, the electrons gain energy because of the fire, they go up in an energy level, and then when they go back down, they release some light. And that light release is what causes things like fireworks to have different colors. So depending on what chemicals you put into the fireworks, they're going to produce different colors because of this. So if we take a look at the type of light that these, say, like fireworks give off, the fireworks are going to give off a range of different colors around here. So let's say it's like a purple firework, right? If it's a purple firework, and we take a look at the spectrum, pretend all the rest of the colors are filled in here. If it's a purple firework, so something like around here, and we take a look at the spectrum of light that's produced by this chemical giving off light, we're probably going to see a peak or a higher intensity of light coming out from the purple place. We might see some light coming out from other parts of the visible spectrum, but primarily we're seeing it from this purple part. Yeah, it's really neat. Does everything give off purely visible light, or are there some that are infrared? But yeah, I mean, if you take a look at like the full spectrum of light that these things give off, again, it depends on what these energy level differences are, or like how it's actually like moving between these energy levels, because there's a bunch of different crap that can happen in between here. This is like the very simplest example of what can happen. There's also like other types of radiation of energy, etc., etc. But yeah, depending on what these energy levels look like and how much energy you're injecting, stuff like that, the type of light that's given off can be different. Like you might actually get some over here, you might get some over here. It all depends on these energies. Yeah, if you've seen it before, anything like the next level below the red light in terms of energy, this is the infrared. I'm pretty sure after that it goes into microwaves, and then you get like radio waves over here. So like the radio waves that are traveling to like that we use for radio, those are all down here in terms of energy. And then, as you might have guessed, if it's higher energy than the violet light, this is where our ultraviolet is. Yeah, exactly. So ultraviolet, the reason why it's penetrating your skin is because it's higher energy. And if you take a look at the relationship between energy and wavelength, you might imagine that something that oscillates faster or like vibrates faster is a higher energy. So you're going to see a bunch of like that for the wave, and then for the wave of light. And then the lower the energy you get, the longer this wavelength tends to go. So these, like the radio waves, those are like some pretty huge wavelengths. And then yeah, the VUV, some of these wavelengths can get straight through like skin, that kind of thing. I think generally most of your visible light isn't going to be able to penetrate skin, but don't take my word for that. I would look it up. And then you keep going on the UV side, and then the highest level that you'll probably see is gamma rays. So like the Hulk, when he got hit by gamma rays, those were this like high energy level of radiation. And yeah, so if you take a look at where these intensities are, where like these peaks are for how much light a molecule will give off, you can usually either find out certain things about what this looks like. So like where these energy levels are, you can take a look at how easily these electrons can get bumped up in terms of energy and then go back down in terms of energy. You can use it to help identify certain molecules. So like some versions of this kind of like spectrum thing, depending on where the peaks are, you can actually tell what some of the parts of the molecule look like. So typically for like, let's say like, yeah, the peaks are upside down for this, but for an IR spectrum, infrared spectrum. Where these peaks are can tell you what types of what we call functional groups are on organic molecules. So organic molecules are ones like alcohols. We have some like ketones. So acetone, for example, is a ketone. Acetone as in like nail polish remover acetone. We have, let's say, like alkanes. This includes stuff like propane, butane, and all of these have like characteristic functional groups. Alkanes are pretty much just like, they're just chains with nothing. They're just like C's and H's, carbons and hydrogens. The ketones, I think it's like this. Ketones look like that. And so like for an alcohol, the OH is what we call a functional group because it adds like a function to the molecule. The ketone, this O in the middle is going to be your functional group. And yeah, depending on what these functional groups look like, they're going to give you different peaks that occur. So you can look at the IR spectrum. You can use a table of the values for like, oh, this frequency corresponds to this functional group. And through this, you can actually tell what the molecule might look like, which is pretty darn cool. You'll typically run into this. IR you're going to run into in organic chemistry lab because you're going to be working with these kinds of molecules. You might also run into like NMR, nuclear magnetic resonance, which is a different method that also sort of kind of looks like these, looks into these peaks. For characterization of molecules, so like figuring out, like someone hands you a molecule and they're like, hey, please tell me what this is. To do that, that's the job of an analytical chemist. So analytical chemists will pretty much quantify and also identify what you have in your sample. So you hand your sample over to them, and then they should be able to help you figure out what's in it. If you want to be employable within chemistry, you want to go into analytical for the most part. Analytical chemists are very often unsung heroes in the chemistry world, because a lot of what they do is very technical, but it also sounds like a technician's job, instead of like a usual like chemistry researcher kind of job. But like real ones know, analytical chemists are like everyone's best friend. You see how I got no, this is still undergrad stuff. This stuff is still undergrad, unfortunately. My stuff is, yeah, the PhD stuff is kind of just a lot more. Yeah, but the reason why a lot of this probably isn't easily understandable is because of not knowing the background. Like, yeah, if you know the background of this kind of stuff, it's definitely a lot easier to understand. So the stuff that I'm going to be looking at is mostly going to be UV vis spectra. So UV vis spectra, as you might be able to tell, include both UV and the visible spectrum. And the molecules that I'm going to be taking a look at are lanthanide complexes. So if you take a look at the periodic table, there's typically this like insert that's cut out, and there's this like separate 2 rows of chemicals at the bottom of the periodic table. These are called lanthanides and actinides because, funnily enough, we have 2 elements over here. One of them is called lanthanum, the other one's called actinium. And because these because these elements follow after lanthanum and actinium, that's why they're called lanthanides and actinides. Now, what's funny about these is that they have quite a few electrons. So if you have more electrons and you have light shining on those electrons, all these different electrons that they have can keep bouncing between these energy levels. And sometimes these energy levels are pretty close together. Like sometimes this gap isn't that big. So just some light is gonna send these electrons all over the place. So not only do you have to keep track of more electrons, you also have to keep track of a bunch of different energy levels. So this kind of energy level thing, like you might have like this, and then like tens of different energy levels up here, and all these electrons can go to any of these energy levels, and you have you have all these electrons. They're all gonna be like all over the place, right? They're gonna be all over the place. And then when they drop back down, you have all these different energy levels, and they keep dropping back down, and you have a bunch of different types of light that come out, and you're like, what the heck is happening? So you might be able to already see like this type of situation makes things a lot more complicated. So then your spectrum is gonna look, it's not gonna look like terrible, but you're gonna probably see like a bunch of peaks. Well, let's say like this. Right? You're gonna see a bunch of peaks. And if you're just doing this experimentally and you only have this UV vis spectrum to go off of, you're gonna have to try to resolve these peaks, as in like try to figure out where the peaks are, how many of the peaks there are, and which one of these, like all these random crud transitions these peaks correspond to. And just doing that itself is a pain in the butt, unless you really know what you're doing. And even if you know what you're doing, sometimes this kind of stuff, like you don't necessarily know for sure. If you're like, you might have a guess, but you don't know for sure. And then if you talk to like a computational chemist that can generate these UV vis spectra, what happens is like all these different types of light that come out, the computational chemists can simulate that. Like they can simulate what types of light should be coming out, and with how much frequency and strength these different jumps and falling back downs should happen, or how often these like different jumps can happen and how often they happen. So all these different types of amounts of light that can come out, the computational chemists will probably generate like all these different peaks. So all these lines are these transitions of like electrons' energies dropping back down and then going back up, yada yada yada. And the computational chemists, because they're able to generate what these like transitions should look like, they're probably going to be able to tell you what the transitions actually are. So like what energy level is the electron being bumped up to, and how much energy is it releasing when it goes back down. And the computational chemist, when they get their transitions, they can also generate their own idea of what the spectrum should look like. And it's I've never seen it match one for one. So they might see like a spectrum that looks like that. And if there are any features that look similar, so like let's say, okay, this peak and this peak look pretty similar, this peak and this peak look pretty similar, you're kind of able to you're kind of able to tell for sure, oh yeah, this one, it's probably like this type of transition, and it happens this much. So having the computational and experimental matching is pretty nice, because the computational side is able to give you a better idea of how this molecule is supposed to act theoretically, and then when you do it experimentally, you're able to see how it actually acts. And then if they agree pretty well, then yeah, that has its own like set of analysis. Hello, Nanashia. Welcome in. Thank you for the health check. I have wet myself. Yes, very notes. Badly explained. Very, very badly explained. Because these pictures might not even be anywhere close to what it actually works, or how it actually works in the science. Unfortunately, I'm already more than half a year out from doing this. So I need to, and I never learned it properly in the first place. So I would need both a refresher and also an actual like lecture to tell me how this actually works. So yeah, so there's different things, there's different features of this type of UV vis spectrum that I could test as like the observable, or the all those different names that they had for the Y variable, I already forgot. Target variable. So this is where my machine learning stuff is going to be focused on. It's how can I predict any of these things by just looking at what the chemical is and what information on this website called PubChem is available. So like, let's say like molecular weight, we could say like boiling point, we could say density, all these different variables. If we have these variables, and let's say like what are, I'll talk about ligands really quickly. What type of ligands are attached and what the metal center is. We have all this information from a database from PubChem. Can we use this information to predict what this thing should look like? Any part of this. So like, let's say that this is a D to D transition, so that the D is the type of energy levels So it goes from a D energy level to a D energy level. That's a D to D transition. For this D to D transition, we could say like, what is the oscillator strength? Which is the oscillator strength. It kind of tells you how readily this specific transition occurs when you have the light shine on it. Or like, what was the other one? There's just like one length variable. There's two ways of representing this length, but there's like this one length variable that can pop out. Or like, let's say, oh, I want to see if one, this D to D transition pops up, and two, if this like pi to pi star transition happens. Again, pi to pi star is just the different types of energy levels. So it goes from a pi energy level to a pi star energy level. Like we could predict, oh, do both of these occur depending on all this stuff? Or what is the oscillator strength for this specific transition based on all this stuff? Or like, what is this length thing for this transition based on all this stuff? And the paper that we took a look at last week had something, it wasn't like the UV vis spectrum, but it was still like, what can we predict about the molecule based on all these different variables down here? Like petrified wood. Did you know that trees were so old they were there before bacteria that could break them down? That's why some very old trees turned to stone. I did hear about that, and also that sharks are older than trees. Alright, Mario, have a good sleep. Have a very good sleep. Yeah, I hope I hope. Oh wait, also, I was messaging Obtuse Corner, a friendly, before stream started. I don't know when Obtuse is. I mean, Obtuse is still recovering from something. So once he's recovered, he might return to stream. But yeah, he shared a couple photos. I'll maybe hound him to share them on the server. Yeah. Actually, oh no, I ate plenty. I ate plenty tonight, but thank you for checking. Yeah. Yeah. Thank you for coming in. Congrats on first again. And I'll see you whenever you're able to pop on by again. Okay. So last thing before I actually start getting into the stuff I need to get to. There's a pantry. Oh, heck yeah. I was watching a video about how many different cuisines and like ways you can spice up your life with cooking, just based on different spices you use, and how I guess like human cooking evolved based on what these mixtures of spices are. And like, yeah, anytime you have a different set of spices that you use, it can give rise to a completely different cuisine, like a completely different dish, which is super cool. Yeah, I'll hopefully post a couple of my dinner things from tonight on the server afterwards. Okay, so ligands and metals. Alright, have a good night, yo. Have a good night. Okay, so these lanthanides and actinides, these are counted as rare earth metals. Yeah, so these are still metals, even though they're kind of like this insert that's taken out of the metal section of the periodic table. Sorry, this is the metal section. And these are also metals. Actually, metal section I think is like here. Noble gases. I think like... I think it literally just start. Actually, all these are metals. Transition metals. Transition metals are here. Lanthanides, actinides are here. What did you miss? I don't know. I honestly can't tell you. I mean, the gist of what I was saying was just my stuff is going to be like, what about this kind of plot would I be able to predict by using information like this about a chemical? And specifically lanthanide and actinide complexes. Yeah. So the complexes, these are molecules that can form between metals and what we call ligands. Let me see if... Yeah, so stuff like hemoglobin. Hemoglobin's the iron-based molecule that transports oxygen for your blood. Those are coordination complexes, or complexes, where you have a metal in the center, and surprise, surprise, we call it a metal center, and there's going to be stuff attached. It might look like a butterfly, it might look like a circle, it might look like just like, it might just look like some little things that are attached. But these are our complexes, and for these complexes, at the center of them we have the metal, and then we have things attached which we call ligands. Now, depending on what your metal center is, so what metal is at the center of your molecule, and depending on what these ligands look like, and depending on what's surrounding this complex, so like let's say it's water. I don't think most experiments are going to have anything in water. You could have like tetrahydrofuran, THF, whatever solvent is on the outside. These can affect how this complex behaves. So that's why we want to consider what the metal center is and what the ligand looks like. Because these directly affect whatever thing we want to look at. Thank you for hydrate. Alright, wet myself. Thank you, thank you. So, the first thing I'm going to have to do is figure out what I want to look into. So let's say there's like, unfortunately, like I don't have much like that much of a background in this stuff. I only studied a few things. No. Yeah, I'm just word vomiting. I swear, if I like actually prepped the talk about this, that started from an earlier point in discussing what I'm discussing right now, I can guarantee that would be easier to understand. But again, it's because I'm jumping in straight from. It's not you, it's me. No, it's not. It's not you or me. It's the fact that you haven't learned it before, so I can't really explain it. I can't really explain it in full, and I haven't taught it before. That's a big thing. I haven't taught this material before, especially because I don't have the credentials for it. Yet. I don't have the credentials for it yet. You just arrived unprepared. No notes. It's time for your test. Yeah, I think one of my weaknesses when it comes to explaining things is trying to explain them off the cuff. I typically like to prepare how I'm gonna be explaining things and have like analogies to make it easier to understand. Because if I already know like things that anyone off the street would know about this stuff, or like connected to things that they already understand, then that's perfect. If I don't have that, then I'm screwed. And they're screwed. You know, I'd be a teacher. I would if it paid more. Yeah, pretty much I would if it paid more. But at least like keep myself afloat in terms of money before I find a job. Yeah, the plan is for me to tutor. Yeah, so my game plan is see what other people have done when it comes to the UV Viz stuff. Then I'm gonna have to probably choose like what kind of transition is pretty characteristic of these types of complexes. I also have to choose like what types of complexes I want to take a look at, because I want to make sure that there are ones with like enough examples of having these ligands. Like if it's only one molecule with a certain ligand, that's probably not going to help my case, because it's just like an outlier that doesn't do much for like predicting stuff. So yeah, I need to choose this transition carefully. I also will probably end up doing an auxiliary strength thing, because this has its own like easily interpretable meaning. Teaching's difficult. Some people lack curiosity. I mean, it's fine if they don't want to be too curious about stuff, but as long as they're like willing to put in the work to learn it, then I'm always open to working with them as much as I can. Yeah, like students who came to my office hours, even if they weren't as good in the class, I would try to help them out as much as possible. And pretty often, like, the ones who came to office hours more actually did do better in my class. Yeah, but teachers criminally underpaid. Absolutely criminally underpaid. For the amount of work that they have to put in outside the classroom too. classes over the summer themselves, all the crap that they have to take. Bureaucracy, administration. Not my cup of tea. Okay, and then I also have to take a look at what information's actually on this PubChem database. What's available for me to model things off of. It's just going to be another slog. Yeah, thinking about it, the amount I'm going to have to look into this stuff is actually turning me off a little bit. But if I can't even do this, then how can I do it in an actual work environment? I gotta learn it. Okay, yeah, so that's my quick, like, very quick rundown of what I'm gonna be looking into. I was a TA for a grammar class at my university. After I explained, I always asked if they had any questions. They said no about an exam, a lot of no basic stuff. I know, yeah, I know. Yeah, I think it's one of the things that I picked up too late in college, because people always have the thought that they don't want to hold up the class, even if the question is like good and it would help more people understand stuff. Yeah, a lot of the times it's just like social anxiety, as well as not wanting to face judgment for not understanding things. And I guess like sometimes even a lack of being willing to look dumb. Like they're fine with being dumb in private, but like in public it's harder. And most of all, I think it's because a lot of people just don't know what question to ask in the first place. Because sometimes you do need to understand something well enough just to frame a question at all. Or it's like, oh, I don't understand it now, but I'm gonna read up on it later when I'm studying. And then when I'm studying, I might be able to figure it out. Yeah. But yeah, I have had like, I mean, most of the time, the students that did poorly in my class, they did poorly just because they didn't understand the material well enough. And I'm only really gonna help someone if they actually ask for help. Like in the actual, let's say it's like a laboratory course. I'm going to be making my rounds as they're doing the experiment and asking if they have questions and stuff. But like if it's on the assignments themselves, unless they ask me something, then yeah, I don't know that they need help in the first place. I think they're just not feeling like it. It's pretty much, I leave them to be the driver of their own education. Yeah, I think that's the best way to put it. Yeah. They have to drive their own education, especially in the college setting. Sometimes we don't understand what we don't understand. Yeah. And sometimes for like a scientist especially, it's really important to understand what you don't understand, because otherwise how can you formulate the questions that drive the science itself? Yeah, the one time I had a student where it's like, yeah, no. It was because towards the end of the class, yeah, she was already doing poorly, but she came up to me with like a question about one of the lab reports, and I brought up the lab report rubric. I brought up the rubric that we use to grade. So that I could reference it, and the student had the audacity to ask me to like send her a copy of the grading rubric. I'm like, why would you even ask that? Of course not. Yeah, and like, I couldn't even tell if they were trying in the class. Like, if I see that you are giving it an honest effort, okay, yeah, if a student is giving an honest effort but they're still not doing well, yeah, I'm gonna talk to them. I'm gonna literally be like, hey, I have officers at this time, and this is something no other TA is gonna do, because most TAs are not gonna be quote unquote wasting their time. But like, I will literally schedule a time outside of my office hours to just meet with a student online or something and help them individually. If they can't make it to the office hours, I'll make time. I'll make time to help you out, but you need to show me that you're making an effort, so I have the drive to actually help you out. Or like even ask you if you need extra help on my own. Yeah. Like, I literally don't think I've ever had a single TA that would schedule time outside of the office hours. They would probably just say like, go to this resource or go to the professor or something. Yeah, because like I have a pretty vested interest in making sure the people in my class pass. Otherwise, I'm a bad teacher. Yeah. I'm gonna hide this for a second so I can bring up my notes. Let me hide this. Yeah, I wanted to take a look at this again. Oh wait, I definitely want to look at this one. Okay, so choose a specific transition or transitions. Determine the auxiliary strings. So again, this one use random forest, KNN, support vector machines, kernel ridge regression, multi-layer perceptrons, and adaptive boosting. Thousands of experimental values. So I'm probably going to want to look at like a pretty big data set if I can. I'm also wondering how much computational power is needed for running these, because if I can run it on my local machine, then that would probably be ideal. I mean, my laptop is pretty strong, so I don't think it's out of the question. I should be able to do this on my laptop. Identify molecular, metallic, and solid features most relevant to binding affinity. I did take notes on this already. $698. 698 ligands. Oh, that's a lot of ligands. Okay. That is a lot of ligands. Any properties, the metal ion or the medium? On the class of ligands or metal ions only. Thank you for another hydrate. Let's go. Glug, glug, glug. Thank you, thank you. Glug, 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 glug. 698 times 15, 698, 349, 349. So there's like 2,000 or so. Okay, so not every cation had the same ligands. Otherwise, we just have a clean 15 times 698. 8 solvent media, so even less than that. Actually, I'm not sure if people would do the same ligands in different solvent media. The molecular descriptors used in this study comprise both physiochemical and topological descriptors. Topological indices. Descriptors were augmented with properties of metal cation and solvent medium to factor in experimental conditions. An out-of-sample model validation was performed on 6 nitrogen donor ligands with known binding affinity values. Having tested generalizability of our framework, we employed the best performing regression model to predict binding constants of lanthanide metals with nearly 71 million molecules. Yeah, I'm not doing 71 million. What in the heck? Yeah, what is their testing? 102 descriptors is a lot too. Six scaling. Auto feet for nonlinear. Linear regression generally failed. Did I write any notes on the Pearson correlation? No. Lasso L1 based sparse feature selection technique. The returned subset of descriptors neither include the most important features nor the metal and medium related properties. See. The dataset itself had these binding affinities built in. Man. This is tough. There's a lot to consider. Okay. This one's a bit more recent. And by a bit more, I mean a lot more recent. So 2019, right? 2018? 2020. Okay. Oh yeah, 2025. Wait, is this the one that's... Oh shit, this one's locked. Individual atomic transition probabilities known as Einstein A coefficients for each emission line. Let me see if I can get it off the institution website. Log in. Please let me still log in. I need VPN. Oh my god. let me see if it's on archive. They didn't post on archive. I need to see this paper somehow. Sorry, just trying to find a way to see this paper somehow. Worst case is I just try to find another paper that's similar. Wonderful. Okay, I guess I might need to just find another paper. They're using genetic algorithms here. Probably not what I want. I think I'll take a look at this. This one's on Chem Archive. So very small. Each of them are very small configurations. These are weakly dynamically correlated. Because of the large weight, it's reasonable to optimize the orbitals for leading configuration only, run some truncated CI calculations. If they're multiple of the same weight, no longer reasonable to optimize orbitals for just a single configuration because it's biased towards that. Those are not necessarily related by single or double excitations. So CISD might not include all of them. You have active space with strong static correlation. Basis is numerically complete, but truncation leads to errors. The term multi-reference then refers to a calculation where all or most of the CAS SCF configurations are used to generate excitations from. How do you actually measure the character though? So you have to actually do the expansion. Or at least with an SAF level. Not well described by single configuration or Slater determinant. Number weighted electron density. Fractional occupation. Can be done semi-empirically. UHF for the active space. Significant fractional occupancy of the UHF natural orbital indicates that the orbital should be included in active space. Okay, so I am not doing that. No, it's another LCVA. Oh my god. Oh wait. Ceramics International. Did not know that's a journal. Isn't it cool that there's a journal about ceramics? That's super cool. Optimized extreme gradient boost and light GBM for predicting Judd of felt parameters and rare doped phosphate-based classes. So I guess maybe it might be worth it for me to just go straight to XG boost and light GBM. I mean, idea-wise, I think I'm almost there. I do also need to see what information is actually available about these complexes. So let's see. Okay, yeah, let's take a look at oscillator strengths, I think. Molecular chromophores place only about 1% in the UV vis range, so individual chromophores operate about 1% of their theoretical limit. We explore the distribution of oscillator strength as a function of excitation energy. To the same, we use familiar independent electron model Hamiltonians as well as first principles electronic structure methods. While model Hamiltonians capture the qualitative electronic spectra associated with pi electronic chromophores, these Hamiltonians mistakenly focus the oscillator strength in the fewest low energy transitions. Advanced electronic structure methods, in contrast, spread the oscillator strength over a very wide excitation energy range, including transitions to Rydberg and continuum states consistent with experiment. Our analysis rationalizes the low oscillator strength in UV vis spectral region molecules. Step towards the goal of oscillator strength manipulation and focusing. they're using computational. B3 lip. Yada 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 yada. Anything? Okay. These are all just theoretical studies. Huh. This is actually... I don't think this is like that standard. Directly telling you which orbitals you're going from. I mean, in most analyses, you'd probably see something similar to this, but you probably... You're probably more often gonna see them like tell you what the names of these orbitals actually are. They're not just gonna say orbitals, they're gonna say like this number orbital. What? Is this worth doing? What? I guess it's like a toy model. Yeah, I mean, if they're doing Hugel model calculations, then that's definitely... They're definitely like an organic chemistry lab. Who's corresponding author? Oh. So they do study organic molecules, but why use these? Oscillating strength is somewhat less concentrated in the home of the limo range, especially for longer chains. 40%. STO3G, what? Why are you doing this? What the heck? Sorry, I'm trying to think of why they would run these super low level models. Like this one I can somewhat understand. This one is like an organic chemist's way of looking at this stuff. That isn't actually like that accurate as far as I know. But what's getting me is the STO3G basis that they're using here. What the fudge? Okay. Do they explain why they use this? It's also classified by the types of electronic transitions. 2DFT is a full electron approach. An expansion of singly excited configurations. Oh, they're looking at oscillation. Okay, okay, that makes a bit more sense. Okay. They're just using it as a way to look at how it behaves in these reductive models so that you kind of like remove a bunch of other variables. That's as far as I can imagine they're going with this. So just simplifying the model and focusing on just the comparisons. Labels positive class, relate the photoreactive potential. Mole extinction coefficient above 1,000 liters per mole centimeter. Negative if no such peak is in the list. Random forests were selected among several algorithms. Machine learning output UV-Vis spectrum class was explored as a predictor of the 3T3 NRU phototoxicity in vitro assay for a set of 43 molecules. So we have an external test set, and then we have a prediction set. Comparable results were observed with the classification directly based on experimental UV-Vis data in the same format. Virtual molecules. Let's also read over this. chemical phototoxicity is if there are certain chemicals that you usually use that causes reactions in your body. Okay. That's just by name, that's pretty concerning. So I can see why people would be interested in studying it. First absorption, peak position, bandwidth and extinction coefficient, emission peak position, bandwidth and photoluminescence, quantum yield. And illustrated possibilities of applying machine learning to find target molecules with desired optical and photophysical properties. RMS errors of the predicted values are found to be 26.6 and 20.0 nanometers for absorption emission peak spectrum. Peak positions. It's not terrible. I think that was somewhat within the range of what's expected. I think. Is it? Better prediction by the ML model. Someone messed up. A typo in a reference. And it's better than missing a reference, but gotta be careful. They can be trained with theoretically calculated datasets obtained, for example, by DFT. ML models based on theoretical optical spectra, pre-calculated by FTTD for gold nanoparticles and nanorods. Okay. That's pretty dope. Okay, yeah. it's been dumb. Training them to predict full UVA spectrum requires large databases of spectra obtained under consistent conditions to predict multiple continuous variables. Classify organic molecules in terms of UV absorption spectrum based on molecular descriptors. So rather than predicting the full thing, they classify them. I mean, that should be less intensive, right? Positive nano classes related. Okay, so this is their like absorption maximum is reported within the UV viz. Reaccess database. It's oh my god. Why is it LSVA? Okay. LSVA, why? Why? Anytime I see that website come up, I'm like, I'll never be able to see this ever in my life. Whatever's in here, even if it's a gold mine, I'll never be able to see it. Because they monetize the crap out of everything. Okay, so this is an important part. Focus on classification of molecules based on whether or not their maximum sorptivity peak occurred in the UV vis spectrum. So positive if yes, negative if not. They use the Reaccess database dataset. Selection. Crimson, hello. How was the rest of your stream? I hope you got through many chapters. I never ended up finishing even my first route because I lost track of everyone who I wanted to have end up together at the end. I mapped. Let me see if I can find it. I literally, when I first played Three Houses, so I'm coming from Fire Emblem 7, and I do still prefer the GBA games. Yeah, sorry, I couldn't actually stay for long at all. Yeah, it's long. Let me just copy what's on here. I'll copy it into a new. So this is my spreadsheet for my first run. Unfortunately, I don't know how to read this table anymore, so I can't tell what I was doing here. I think done means that I think this means that their support already reached where it was supposed to go. I don't remember what the stars mean. I think, yeah, I was gonna put together guesses for the original pairings that I wanted. And I like overtrained everyone to boost up their supports. So whenever I get back to that first run that I did on Blue Lions, I will have literally no challenge whatsoever for the main maps. I might end up just keeping the supports as they are, and then just ignore every other one. Blue Lions best house. Yeah, I think because I chose them first, I have like the specific bias that they're my favorite house. Yeah, and on this route, or on this like first run, I recruited everyone I could possibly recruit. I really want to finish the game someday. Yeah. Also, they're just the best. Yeah. I got to see a bunch of the voice actors at Anime Impulse back in 2020. So like, yeah, that's around the time the game was released, right? So in total, yeah, it was really cool. In total, I think they had like they had Chris Hackney, so they had Dimitri, Dedu. I think Felix's was there. Sylvain. Bernie. And then Dorothea and Shamir are the same voice actress. Rest in peace to Ferdy's voice actor. Petra's, Marianne, Leonie, Flane, Sedith. I think that's all. Yeah, so there were like 12 of them. 12 of them that all attended. And at the time, oh wait, and Ignaz's, Christian. Yeah, and at the time, I think it was Christian's first ever meet and greet event as a guest, which is also really cool. And by now he's been doing like directing and stuff. Yeah, but eventually I'll finish this. But there was a run that I was started on YouTube back when I streamed on YouTube, And then I think I tried to do a little bit of it on Twitch, but it's a more restrictive Byleth solo run, and I don't even actually know if it can work. I still need to do a bit more research into it. But the idea is not even allowing any of the non-Byleth characters to enter combat. Like, if any of them enter any combat whatsoever, then I had to restart. But on the level after time skip, where everyone comes back, I don't know how I'm gonna do it in one turn. Like, I don't even know if the garrison, I forgot what they're called. The little armies that join you in battle. I forget what they're called already. Yeah, I don't know if I can get the authority levels up and actually have them learn battalions. Yeah, I don't know if I can actually get the battalions to just let me move Byleth all the way up to the boss immediately, because otherwise the run literally can't continue. Yeah, so as long as they're able to get a garrison for like the dancer garrison, yeah, then I'm screwed. But we'll see. Only one you've met is Hubert. I want to know what Hubert's VA thinks of Hubert. I feel like that's a psychology experiment in itself. Yeah, the challenge runs, I think this one was done by... I think the Byleth solo that I saw was done by Mecha. But Mecha's run had a few quality of life rules that were attached so that it would actually be more possible to do it. Yeah. And if you ever see Avior Red in my chat, that's AYVUIR and then the color red. He's also a Fire Emblem enthusiast and certified Three Houses hater, but he's playing Three Houses. He's been streaming Three Houses. He thought it was very funny when I said that he was my favorite role he did. He was a little taken aback. There's a difference between hating on a character, which a lot of people do, and then doing a good job with it. If Joffrey did that good of a job on Game of Thrones, to the point where he himself was hated outside, even though he's literally not even Joffrey himself, and that tells you that you did a good job. As bad as that situation was for the actor, it does go to show how well he did the job. The Mega Evolution to Violet Silver Run 2 was very fascinating to watch. I need to... Well, okay, yeah, I need to complete the game so I can actually watch these runs in their entirety, because I don't want to get spoiled. Yeah. I've also still been sitting on Path of Radiance since I was a kid. I tried to finish it as a kid, I didn't, because, yeah, I was still too into the Game Boy ones. and then the Game Boy releases. And then around college, I came back and I tried to do it again. But then I think it was just because I had to go back to college after a break. I wasn't able to finish it again. Maybe third time's the charm. And it's one of my friend's favorite. So if we can gush about it together, that'd be amazing. Yeah, but I don't have a Switch 2, so I won't be able to play the newest one. All the 3DS releases I wasn't able to play either. Okay, I'll get a few more notes down, and then, yeah, 4 minutes until I call it for the night, because I have a Star Rail event to finish. I didn't realize the Star Rail event for Fate was tied to the story this time. So I've just been sitting on it without realizing. And now that it's almost over, I realize, oh, I had to actually play through the story to play the event. And now I don't have time. I even took my first steps into Shineznaya, even though I'm still back in that land for Genshin. So I could do the event that ended last night. And then I got up like 5 hours later, 4 or 5 hours later, to join my dad when he showed me the stock stuff that he's doing. Yeah, I'm a tired boy today. I'm a very tired boy. Oh yeah, and 2 nights ago? Yeah, 2 nights ago, I was trying to learn Tony Tran choreography. Tony Tran from Cabin Modern The Kinjas. And let me tell you, I knew his choreos were going to be hard, technically, body movement wise, but I didn't realize exactly how hard it'd be, because he's doing like super technical movements, but also like super quickly. Like if you watch him do his choreos, everything looks really chill, small, relaxed, not too much intensity. But when you're actually doing it yourself, it's so hard. It's so hard. And then yesterday I ended up with like a stiff neck. A really, really stiff neck, to the point where my dad had to help like massage me. And then I needed Salonpas on my shoulders. It was really bad. Salonpas goated. Okay, I'll at least take down the notes for the dataset selection. So they had molecular weight, filter, 1 fragment, single fragment. I think single fragment should probably mean that the ligands aren't too far away. Because if the ligands are far away, then I think it would probably be considered 2 separate parts. Or if you had like coordination chemistry, or like it's all coordination chemistry. If you had any like waters that were surrounding your molecule, if there are any waters, then yeah, that would probably be counted as a separate fragment. Methanol as a solvent, I think, is relatively popular. Exclusion of molecules with metal atoms. Oh, they did organic compounds. Wait, did they do also your strengths then? Oh no. Random forest. Feature importance. Oh. Okay, this is not what I'm looking for. Yeah, this is not what I'm looking for. Shoot. Did they do? They also did organic compounds. Mother, father. Mother, father. These are all organic. Okay, well, I mean, it doesn't have to be perfect, so I can just, yeah, I can just run with structural properties. Okay, yeah, so tomorrow we're going to be figuring out what set of data to be using. I'm going to look over this oscillator strings thing, and then I'll try to get started on cleaning up the data, or at least like, yeah, I'll try to get started on cleaning up the data, or at least like setting up the Jupyter notebook environment for running the calculations. I don't think I need this. Yeah, this is just for fun, drawing out what we're doing. Okay. Oh dang it, Clarky's ending. Okay. I think we're headed over to Wombat for today, because I think it's been a minute since I last raided over to him. Alright, yeah, let's just send it there for tonight. We got the raid messages. I gotta do that star rail thing. I really gotta lock in and get that done. Alright, thanks to anyone who joined. This has been Orcla. Hope you have a good rest of the night, morning, afternoon, or evening, wherever you are in the world. And I'll see you on the next stream. Bye bye.